afternoon, everyone. Thank you for joining us today. So we will have another 3 minutes. We will start. Thank you.
Gathering emphasizes our collective agreement on how important water is at the global level.
A niche conference to position itself among its peers in the overly crowded traditional water shows and conferences we see today around the world.
Meet our existing customers and potential customers and key stakeholders in the Malaysian water market.
This is definitely the show participating in Asia, the big hub for non-urban water solution.
Good afternoon, everyone. I hope everybody can hear me. Can everybody hear me?
I can hear you. I can hear you.
Okay. Hi, everyone. So welcome back to the Malaysian Water Association and Malaysia International Convention webinar series. And how time flies. So today is already our 11th webinar. Thank you to so many of you who are strong and regular supporters of our webinar series. So I hope you've enjoyed what we have done in the past, and you will also enjoy today's session. And today we are pleased to have with us Dr. Eddie Wong, General Manager, Business Development and Technical Support, Taliwas Corporation, Berhad. Dr. Wong will be sharing with us on the topic of coagulation assisted ceramic membrane for water and wastewater treatment. During the midst of his presentation, again, as usual, we'll pull up some poll questions. So please support us by answering those questions so that the Malaysian Water Association can gather this data to represent the water industry to the government and regulators on this subject matter. So after the end of the session, we will have our Q&A. So for those of you who have just joined us, at the bottom of your screen, you'll see an icon Q&A. So you can just click on that icon and key in a question that you want to ask Dr. Wong. Okay, so now I'm going to invite Mr. Lee Kun Yu, Executive Director of the Malaysian Water Association, to say a few words to kick off the session. Mr. Lee?
Okay, can you all hear me, see me, please?
Yes, can hear you, yep.
Can
Okay.
see and can hear.
Okay, good afternoon, ladies and gentlemen. Today's opening address is actually to be developed by our President, Dato' Engineer Abdul Kadir Mat Din, but he wants to send his apologies today because he can't make it. So I will now read his opening address on his behalf. So good afternoon and welcome to today's MWA organized webinar series. This afternoon webinar is the 11th in the series, and today webinar presentation will look at advanced technology after we have touched on so many other subjects. So today we look at advanced technology again. This time we'll be on the topic coagulation assisted ceramic membrane for water and wastewater treatment. It will be presented by our good friend, Dr. Eddie Wong, from the MWA institutional member, Taliwas Corporation, Berhad. It is with the spirit of collaboration and the aim of seeking more resilient water solutions to meet our Malaysian and global challenges that the webinar today shall feature some updates and insights related to membrane applications in water and wastewater treatment by our distinguished water expert, Dr. Eddie Wong. Many of us are aware that both microfiltration and ultrafiltration have become common water treatment technologies for the removal of particles from natural waters. In ceramic membranes in particular, wastewater purification is considered to be the largest application, and analysis forecasts that it will account for more than half of the total ceramic membrane market in the upcoming years. This is due to the growing demand for potable water, concerns about water scarcity, and water desalination processes, which are expected to rise during the forecast period. Membrane is widely used in drinking water treatment in advanced countries in Europe, America, and Japan. Even China now has stepped up their wastewater discharge quality, especially those upstream of River Huanghe. We have to resort to membrane technology to comply with the standards, whereas Singapore is installing one of the largest drinking water plant, the Chua Chu Kang water treatment plant, 180 mld with ceramic membrane. In Malaysia, for example, there are only still less than 10 membrane plants in water supply, and maybe a couple more in the sewage treatment. On the other hand, membrane is almost absolutely required for water reclamation, where Malaysia is at its beginning stage now. As there are emerging pollutants such as endocrine disruptive chemical, pharmaceutical, and personal care products, membrane coupled with activated carbon, nanoparticles, and advanced oxidation, membrane technology are likely shall be the solutions to remove these health concern pollutants. These combined with advanced treatment technology shall be briefly presented and discussed in this webinar. This will focus on the most basic operation of membrane that includes increased flux flow, reduced fouling, prolonged filtration time before clean in place, and the lifespan of membrane in today's topic, coagulated assisted membrane filtration process for water and wastewater. Ladies and gentlemen, innovative membrane separation processes have been constantly evolving and growing worldwide due to the separation efficiencies, reduced energy consumption, low maintenance costs, and environmentally benign impact. Some of the other advantages include resistance to aging, reliability, mechanical stability, even under large pressure gradient, backwash ability, resistance to vibration, better control over pore dimension fouling, effective elimination of additives, environmentally sustainable, and ability to operate at wide operational temperatures, among others. You may wish to put some questions to this to our Dr. Eddie Wong so that he may be able to clarify you further as to all this trend that's coming. It's getting more available and getting more cheaper. Due to all these inherent advantages, they find applications in high demanding applications such as chemicals, textiles, food and beverages, water treatment, among others. Now, scanning the current environment, I can foresee the low demand for new technologies may be coming to an end for at least 3 reasons. The first reason is, of course, that eventually all the existing systems that we have will need to be replaced because they will no longer function properly. And so to do that, we need to upgrade, and that's where the new technologies will be able to make themselves available for the water operators and the owners. Second, with more and more focus on water shortages, water reuse is becoming more popular, and wastewater is a part and a source of this reclamation. The third reason is that with the growth of the electronic industry, there are a lot of new challenges for treating industrial wastewater because they contain things that have never been in industrial wastewater before. There are a lot of new exotic metals that need to be treated. Even though there may be some government regulations on this, certainly it is incumbent on companies to address them simply from the environmental and general liability standpoint. And so in this regard, over the past few years, there has been a shift in interest from the treat to discharge approach to the recycle, reuse, and zero liquid discharge approach. For example, according to what we see today, interest in oil removal technologies is shifting from flotation technologies to ceramic membranes. Biological technologies are focusing more on increased efficiencies and ways to reduce footprint by improving the amount of organics being removed and then take the sludge that is generated and use it to create energy. All of these are aimed at improving reliability, reducing costs, reducing power consumption, being able to get the best quality water back, and then dealing best with the resulting waste stream. Hence, this presentation on ceramic membrane is very timely indeed. Overall, it is foreseen that the scope of future membrane applications will become much wider based on improved existing membrane materials and manufacturing processes. Advanced treatment technologies such as this will allow us to cope with the impact of an increasingly urbanized catchment and the negative effects of climate change on Malaysia's raw water quality. The MWA will support any government initiatives for all water utilities in the country to progressively incorporate innovative and advanced water treatment processes in Malaysia's many aging water treatment plants when they are due for upgrade. Finally, a big thank you to the presenter, Dr. Eddie Wong from TidyWorks, for coming to share some very valuable information on the ceramic membrane technology, and also to our webinar host, ProTem Group. I wish all of us a successful and a fruitful seminar. Thank you very much.
Thank you, Mr. Lee. So without delay, I'm going to call upon Dr. Eddie Wong to start his presentation. Dr. Wong, you can share your screen now.
Okay. All right. Can you all see my screen?
Yes, I can see.
Okay, yeah. So I will start now. All right. Good
Yes,
afternoon,
go on.
everybody. Yeah. So my topic is coagulation assisted ceramic membrane. I changed a little bit, plus the future nanotechnology membrane for water and wastewater treatment, because everybody is asking me what is after membrane. So the upcoming one is a membrane combined with nanotechnology. So my let's go on. Yeah, okay. The outline of what I'm going to talk about this afternoon is first one is what is membrane and types of membrane. Why membrane? That means why membrane needed. Membrane materials, there are many types of materials. Then this is the center, the meat of the presentation, which is the coagulation assisted membrane filtration. So benefits of coagulation assisted membrane filtration. So advantage of ceramic membranes. Membrane coupled with PAC and powder activated carbon and AOP, advanced oxidation process. Nanomaterial and water treatment. And lastly, membrane coupled with nanomaterial. So let's start. So I will, for those who already have a lot of knowledge on membrane, so maybe be a bit patient because maybe some of the participants are quite new to it. So I will start a little bit with the introduction. What's membrane? So membrane is a microporous layer. So our body cell membrane, for example, those are membrane. So the pore size must be below 1 micron. From 1 micron down onward is membrane. Okay. So ultrafiltration. So when you say about membrane, from 1 micron down to 0.1 micron is classified as microfiltration. Ultrafiltration means 0.1 to 0.01 micron rating. Nanofiltration 0.01 to 0.001. So RO less than that, below the 0.001 micron. So in fact, RO is not so much of working on straining. So it is working a little bit on surface tension principle and the pressure. Right. So membrane is relatively expensive for water treatment and the operating cost as well. So but producing excellent water quality. Why membrane? Since it's expensive, because there are pollutants such as Cryptosporidium and Giardia, those are Protozoa. They are toxic algae, for example, Anabaena and Microcystis. There are many motile microorganisms, so sand filter are able to capture them because they can move in between the sand filter. So they pass through the sand filter because they have the flagella, they are mobile, those creatures. For example, Dinoflagella, the red type, Euglena, which is a toxic algae, Copepod, Cradocera, water mites, and others. Later I will show some photo. So membrane will give us a better control and better water quality, of course. Also, because of the emerging pollutants such as pharmaceuticals and personal care products, endocrine disruptive chemical, right? So most of the people may ask, what is the difference between pharmaceutical and endocrine disruptive chemical? So most of the pharmaceutical are endocrine disruptive chemical, and some of the other pollutant, other chemical can be disruptive, endocrine disruptive chemical, ECD. So why membrane drinking water? So this is the situation in Malaysia. Say for example, the pollutant detected in Langat River. So Cryptosporidium and Giardia. So in the study of this UKM, UM, and UPM. So endrine, these are the pollutant. Rodane, all this, from UKM. So and since 2011, so this study from UM and Sana'a University, they detected 15 out of 19 targeted pharmaceuticals, such as mefenamic acid, gropalamide, salicylic acid, metformin, chlorothiazide, and ethanol. So those are the things of concern. That's why membrane is needed. So this is a photo of Cryptosporidium oocysts. This one because they are so-called need very high disinfection level, very high CT chlorine to inactivate them. So we need membrane to remove them because the chlorine, most of the chlorine that we do can't remove them, can't inactivate them. So this is Giardia, also the same thing, and Entomoeba. So this is how it looks like. Also floating toxic algae such as Microcystis, shown in the photo. So it is a type of hepatotoxin, liver toxin. So in WHO guideline, the microcystins, so the toxin from Microcystis is very near, is only 1 microgram, right? So under the WHO, internal and external cellula. That means inside, the total inside the cell and total outside the cell, you only allowed to have less than 1 microgram. So you're very stringent, right? So, sorry, this one is one of the floating toxic algae, Anabaena, just now I have mentioned. So it is producing anatoxin and also microcystin, right? So this is red tide. You can see in Malaysia, in the sea, sometimes it happened in East Malaysia. The sea turned red, and then it's because of this brown algae, Dinoflagella brown algae. So during this season, people cannot take seafood or what they call shellfish because they die, they sink inside the water, and then the shellfish, all those clam, lala, go and eat. So they accumulated the toxin, so it can be dangerous. Sometime in Africa, the whole dam, the normal green algae turned into Dinoflagella. It can be very dangerous. So the other type is a motile toxin algae, Euglena. So they can change their body shape. They can swim. They have flagella. They can pass through filter very easily. So they can what they call struggle themselves and get themselves out from the flop that we're normally treating in the conventional. So so it is a type of neurotoxin. So Chironomid larva, this one can happen because of some what they call insect lay eggs in our filter. So this is in the raw water. Normally this is not see in this one, but this one is very rare. But sometimes it can happen. So Copepod is a type of microorganism. It can be a concern. They are moving very fast in the water, and because they are motile, they also can struggle themselves out of the flop and also can pass through the filter. But what is worrying is inside this Copepod, they can have a type of guinea worm. They call it Dracunculus medinicis. So if somebody is infected by this, this one can infect Copepod and then carry infected larvae inside Copepod. That means the creature just now I showed. So inside the body, they may have this one, they may have the worm, and chlorine cannot kill the worm inside the body of this Copepod. So, this case, in 80s, 3.5 million cases, they found and many African, people blind because of this one. So because the worms, they grow on your skin, you can see like this, and then it will come out like a dana, then it will come out from your leg or other part. If they get into your eye, so the eye is blind, right? So why membrane? So wastewater and desalination is needed because we need to achieve high effluent quality before it gets into the RO, or we need to treat the water to a certain standard, such as in China, we need to do MBR, treat the water and discharge back into Hangzhou. So to remove the total phosphorus and total nitrogen, to remove total organic carbon and achieve silt density index that less than 5 or 3 for RO feed. MBR, they increase activated sludge concentration, the load of the sludge, so that the sludge there's a lot of sludge inside the system. they can eat and then make the what they call treatment, the wastewater treatment much faster, and reduce your footprint. That is the function of the MBR. So without the membrane inside, you can't do that. So you put two in one, it becomes an MBR. So reverse osmosis, you need membrane. Membrane distillation, you need membrane. All this is for desalination. Forward osmosis is also using membrane. So, so if you compare all the technology, most of the technology for desalination, RO is still the lowest energy consumption in desalination compared to other technology. So here I show a little bit of other technology. So you can see, I put a laser, I put a laser point. You can see here. So there are a few technology comparison. So the first one is multi-stage flushing. So this is a combined. This is a MED, stand for multi-effect distillation. So this is MVC is mechanical vapor compression. Then ROED is stand for electrodialysis. So if you look at the whole world, what the installation, most of the installation, more than half of the installation is about 5% of the installation is still RO. So you can see, comparing all the energy costs, RO still are relatively quite low. So the other one new technology coming out is the ED, the electrodialysis. They are slightly lower than it. So, but it's still not many yet in the actual industry installation. So polymeric membrane, there are many type of membrane. So this is one of the material is polymeric. So you can have PAN, polyalkylonitrile. You can have PES, polyether sulfone. You can have PDBF, polyvinyl lydine fluoride. You have PVC. You use PVC pipe. So these are the material can make into membrane. Polyvinyl chloride, very common. Polypropylene, very common. PSF, polysulfone, also you have. PA, polyamide is common. PTFE, which is Teflon, is also common. So there are many other membrane not commonly used for water and wastewater treatment. So in other applications, like cellulose, for example. So membrane material, so this ceramic. So one of the example is the NGK metal water, aluminum oxide from Japan. They already have 170 reference plant. So the second one is the LitTech, silicon carbide. It is from Denmark. So there are already some a few plant. I'm not so sure what is the record at the moment. At least I know Malaysia got this one. So there's one of the operator in Malaysia water supply is having one of these, a small plant in Malaysia. So Attack is from Germany. Maiden is flat sheet. So Jiwu, microsphere and Yixing they are from China. Maybe they are more from China now. This slide may be slightly outdated. Temi industry from France. So there are more and more ceramic membrane in the market now. So membrane configurations. So you can be in the shape, flat sheet. So in this way. So you in the flat sheet, you always need bubble to scrub the membrane surface, so-called to remove the foulant that stick on the surface of the membrane, so that the membrane can continuously filter the water. So hollow fiber is quite normal, it's quite common. Some outside in, like my right hand side one, this is in this, sorry, the thing doesn't move. All right, I need to put on the laser pointer. Oops, it doesn't work. But it's on my right hand side is the outside in, left hand side is the hollow fiber. Right. So they are like more advanced from hollow fiber. After the hollow fiber, you have now getting very popular and many installation, because this multi-pore membrane is what they call is more robust than hollow fiber. Hollow fiber is very easy to break. Once you get choked on the membrane, you know, the mud plucking on the membrane, so the pressure goes into the others, so the hollow fiber will break. So they are not so strong. This one is much stronger. So this is the example of the RO membrane and NF membrane. NF stands for nanofiltration. So they are in spiral wound design. So like this. So they just roll together like the Swiss roll. You have a, you know, you make into a few layers and then roll them together. So ceramic membrane flat sheets. So it looks like this. Now coming back to the example of those ceramic those membrane in Malaysia. So we have a few like Penang, Selangor have two, one in Sungai Rumput, the other one in Kepong. Kelantan have one, Wakaf Bunuf. Hatta Rega, they already have phase 1, 30 mld. I'm not so sure about their phase 2, another something like 30 mld is ongoing. So those are the brand. I'm not going to spend too much time on it. So they some run on upstream clean water, no waterfall, some run on the river water, muddy river water, some run on groundwater like the Kelantan one. So how is the what they call the comparison of ceramic and polymeric? So here, okay, here you can see polymeric membrane, say for example PAN, the pressure can take only 3.5 bar. The PES multi-bore, just now I show, you know, one fiber have 7 bore one. You can take maybe up to slightly more than 10 bar. The ceramic membrane can take above 20 bar. So chemical resistant, you can see they are getting better and better, and ceramic is very resistant. So life expectation is higher on ceramic. Polymeric, depending. PES, now they can go for 10 years or could be slightly more. So the chlorine resistant, you can see this is less than 100 for 1 hour, 100 ppm for 1 hour. This is less than 200 ppm for 1,000 hour. There's no reaction. Ceramic membrane, that means you can continue to put oxidant and filter, there's no problem. So backwash pressure, they can't take so much high pressure. Normally the practice ceramic, they use 5 bar high pressure backwash. You can have instead of using water to backwash the filtered water to backwash, the system can use air to backwash to push out, you know, what is remaining in it. So you can have very high recovery, 98% compared to like 95 or above, or this one, you know, if you even 90 to 95 is quite high. So next, this is one of the case study in 2013. It could be a little bit outdated, but this is what I have at the moment. So the capex, say for example, you compare polymeric to ceramic. Ceramic is more expensive. Say, you know, the operating cost is the same. So membrane replacement is say it's 5 to 7 years. This one is more than 20 years. The life cycle cost for 20 years. You know, if you compare, the ceramic membrane is slightly lower. Even they are more expensive in this case. But now maybe the polymeric membrane is getting cheaper and cheaper. They can be about the same. So this is the main topic we would like to share today. Coagulation assisted membrane filtration. So this is a pilot study done in Malaysia, Turbid river water. So the raw water is from 30 NTU to almost 1,000 NTU. So we run the system. Two types of membrane. One is hollow fiber, PAN. The other type is metawater ceramic membrane. So if you don't use any coagulation, so the flux is like 104 LMH. But the filtration time 15 minutes we need the backwash. You know, the CIP we need to do daily. Recovery we only have 30 to 50 only. So when we put in some polymer into the system, the hollow fiber membrane, okay, you don't do that because this will blind, because those days we don't know, we thought this will be very good, you know, we generate a non-scheduled waste. So the so-called the flux will increase, you know, from 2.5 to 3.5 meter per day. Sorry, I forgot to put in the conversion, but you can see this increase, you know. So the filtration time, you know, we can lengthen to 30 minutes. You know, the CIP we only need to do once a week, and recovery is high, right? Much higher compared to before. So for ceramic membrane later, if we put in PACL, we got 4.5 meter per day or 188 LMH liter per meter square per hour, the flow. No? The flux, sorry, for those who are not familiar with membrane, the flux is the flow passing through the surface of the membrane, you know, per square meter per hour. So that's called flux, right? So filtration time, we can enlarge, you know, we can lengthen the filtration time for up to 120 minutes compared to 30 minutes. So the CIP we need to do is like monthly. So the recovery we can go to 98%. Of course, this 98% we need to have the so-called backwash with 5 bar pressure, you know. So and then followed by CEB. And so this is all in auto system. CEB means clean. CEB means chemical enhanced backwash. It's the same backwash, but this backwash water have some chlorine. Sometimes we have some sulfuric acid. So it will further clean the membrane with less water, right? Instead of many backwash. So when we want to put in some more, you know, we change the coagulant to polymer. So we found that actually it can go even higher. The flux can go even higher with the same condition. So this is what we have conducted in Malaysia, the result. So this is a photo, shows the hollow fiber membrane. So this is how it looks like. This is a hollow fiber membrane. Inside there's a lot of hollow fiber, just like straw inside it. So you can see the raw water. This could be, you know, 70 to 80 NTU raw water. So pass through the membrane, you can see immediately, you know, crystal clear water coming up, which is less than 0.5 NTU. So this is just show the simple system in the box to control the membrane. So how is the ceramic working? So the ceramic working is we have to put in the coagulation in front, so and then we mix a little bit. So we can even put powder activated carbon if we want. So and then after we have a simple coagulation, or now we can use inline mixer and then feed into the membrane system. And in the membrane system, after the membrane system, so the filtrate coming up will go to a tank, so treated water tank or filtrate tank. So for backwash, and the air compressor also for backwash. So all this will get into the, you know, the what they call sludge thickener or sludge tank. As I said just now, if you want to use, if we don't use coagulant or polymer, so the water come out here, it won't settle. So you will have a very difficult so-called concentrate or backwash water to treat, right? So talking about this coagulation assistant, the main key point here is we have to do it without the sedimentation tank. So there are some membrane system, you know, they are doing the coagulation before the so-called membrane filtration. So you have another system. So this one you have a very small system. So it's a very small tank. Only you don't need sedimentation to separate. Once it is coagulated, the so-called the particles are captured in floc, and it is not so easy to pass through the membrane. So this is how the ceramic membrane pilot plant looks like. So we actually can push up to even 7, you know, to almost 300 liter per square meter per hour. 300, almost 300 LMH. But we don't want to report so high for stability. So this is the result. That's how it looks like. This one shows that on this date, we are using the raw water is almost 1000 NTU, but we can still very stable to produce less than 0.2 NTU. So with this 500, we get 0. Even lower, 0.12. So I want to emphasize with the coagulant assisted, the true color is removed very significantly from 22 to 4 or from 43 to 2. If we use any of the membrane without the coagulant assisted, the true color will be about the same. So remember, if we do a true color test in the laboratory, what we do is we are using a membrane to filter, 0.45 micron membrane to filter before we do a color test. So it's the same principle. Without coagulation, the color removal will be very limited. So here we shows UV254 absorbent is like a TOC. It's a simple test. You use UV visible spectrophotometer to do it. So that's how we monitor. To do TOC, it takes very long time and it is very expensive. So this is how we use the UV254 absorbent meter to check the organic the content or DOC, that having in the water. So you can see the removal is very significant, almost 2/3 removed. Okay. So when we use this one is when we use the organic coagulant, which is polymer, then you can see there's no bacteria with this process. There's no bacteria detected, although the raw water we have, but the treated the so-called the filtrate come out the membrane without any chlorine. We couldn't detect any bacteria, E. coli or coliform. So these are the results. So benefits of the.
Shall we stop here for Paul?
Yes, thank you.
Are we midway already?
Yes.
Okay. Okay, so to all our attendees, we pull out the poll question. You can answer question 1, 2, 3, and 4. You can scroll down to see 3 and 4. And then we will put up the results after that. Okay, Henny, are you showing the results? Okay. Here we are. We have you can also scroll down to see all the results of question 2, 3, and 4. Okay, so Henny, what is next on our agenda? Okay, so we have a message advertising slide from our advertiser today.
The voice is very low.
So today we are showing the advertisement from Aracam. So if you see any equipment here that may solve your solutions, your problems, you can contact Aracam. Dr. Wok, we'd like to invite you to start your
Okay.
part 2 of your presentation. I think you need to share screen again.
Okay.
So for those participants who have just joined us, welcome. We have so many people today. Thank you all.
Okay. Can I start now?
Yes, Dr. Wong, you can go proceed.
Okay. So the benefit of coagulation assisted, how it works. Right.
Dr. Wong, we need you to turn on your video.
My video. Oh, nah.
At the bottom of the screen on the left-hand side.
Oh, I can't see.
Bottom part of your screen, you need to press start video.
Bottom.
Left. At the bottom of your screen.
Left-hand side. I can't see.
Left-hand side. Can you see Q&A? The same row as Q&A?
I can't see now because it's covered by something else.
Oh, okay.
It's covered by my something else. Hold on. I need to.
Maybe you can.
He's coming to help me.
Off the slides.
Yeah, the toolbar is. Yeah, it's covered by the two bars. I don't know what happened.
Okay. So maybe you can turn off your share screen first. You can off your share screen first.
On this one. Nothing here.
You can turn off the share screen first. The one.
Because the button is covered by something else. Covered by my normal this one. Now I can't.
Shall we proceed without video? If you have that problem.
I hold on now. Just hold on. I can't.
You can press that one.
I can't. Because it is not to. Yeah, it's different. Yeah, suddenly I can't.
Okay, don't worry about that. Don't worry about that, Dr. Wong. You can proceed without video.
Yeah, people can't see. You hold on. So something is wrong somewhere.
We can see your slides.
You can still see the slide, huh?
We can see your slides. We just cannot see your face. So you can just
Okay.
Okay, continue.
No, I can't even. I have to go to the PowerPoint. You can see the slide, huh?
Yes, we can.
Okay, so I just continue.
Yes.
I just continue. Yeah, you can't see my face, doesn't matter.
Okay.
Yeah. So, okay. Sorry, something happened to my computer just now. I don't know what I pressed. So it covers the thing. I can't see my this one.
No worries.
No, I can't. Hold on. I just off it. Okay, sorry. So how I want to come back to the benefit of the coagulation assisted, the membrane filtration work. So it's actually the coagulation cell or the chemical coagulant. They capture those foulants such as organic and micro particle, which is about the same size to the membrane pore which will clog, which will foul the membrane. But all these particles or organic are captured by the flux. So that's how it works. So, and then the other thing, after they capture, so all these flux, they form a cake, a layer of cake, right? Flux or sludge, such as a cake layer, pre-filter, it acts as a pre-filter. So it will protect the membrane pore. That means you have a pre-filter before the membrane pore. That means you already add another layer of thing to filter. You are not using the membrane pore to filter. You're using the cake to filter, which is the so-called the sludge itself or the flux itself. Right, that's how it works. You can see here in the picture. So there's a cake layer function as a pre-filter. That's how it works. That's how you can get all those benefits. So in summary, if you use coagulation assisted for membrane, so you will have better filtrate water quality. You will prolong your filtration runtime. That means your backwash, you don't have to backwash so frequently. So you will lengthen your CIP frequency. That means you need to do it weekly, then you need to do it like monthly or even longer. So then with that, you will extend your membrane lifespan. So beside that, this will also enhance the so-called treatment of backwash water or sludge. So without coagulant, this one is very difficult to treat. So with the coagulant or even with the so-called polymer, so the sludge will separate from the water. So it's very easy to treat. Now just show you the material, the so-called the membrane that we have piloted, the ceramic membrane that we use. So this is the meta-water ceramic membrane. This is how the membrane looks like. So you can see the so-called slit and all that. I'm using my laser pointer. Okay, the laser pointer here. So the water comes in here, it comes out from the side. It's the slit of the membrane. So next you can see this is the enlargement of the membrane. So this is the channel, the water goes in. It goes in from there, then it will filter through this so-called filtration layer, and the others are the support layer of the ceramic membrane. Right. Now we see how the ceramic membrane plant looks like. So inside all the element of the membrane, one element will put inside one tube here. These are all so-called stainless steel vessels for the membrane. So this is another plant. So this ceramic membrane, 170 are all over the world, in America, in Europe, and in Singapore. The biggest one is in Singapore, 180 mld. So these are the separation, the different generation of those membrane in Japan. Total will be 156. So this is the market improvement of the membrane. So I do not have the update one, I'm sorry. So it's coming out. So the specialty of this type of ceramic membrane, meta water, So it has recorded no membrane breakage for 18 years. High backwash pressure can be applied, even higher. Now it's 5 bar. Normally, those polymetallic membrane cannot backwash with such a high pressure. So therefore, you can have high recovery. You don't use water to push out the so-called concentrate. You use air to push out the concentrate. So because it is ceramic, so it is able to operate with organic coagulant. If it is polymeric, you use organic coagulant, it will blind your membrane. You cannot recover back. Right? So it will destroy the membrane, it will block all the pore. So, and then it will produce, with that, it will produce non-scheduled waste sludge, because the sludge produced is not using aluminium-based coagulant. If you use PACL, of course, it will still be scheduled waste, or alum is scheduled waste. It is low energy cost, and then it will lengthen the CIP interval. It is stable in operation, able to handle search in this one, in the NTU. So it has been full flux recovery for the past 18 years. So here it shows that this is a record for the metawater ceramic membrane, that they can get back the flux after even 18 years. So that means the flux, normally polymeric membrane, after a while, the flux will decline at the same pressure. But this one, it has been stable for the last 18 years, because the ceramic membrane, you can use very strong chemical, acid or alkaline or whichever, to wash it, or oxidant to wash it. So this is an example, they track that even if you using this system, when there's a very heavy rain downpour, so you will, normally other system will have affected, but this system, you can stabilize very fast. You can see the graph here. So in general, advantage of ceramic membrane, so it is low life cycle cost, okay? It is sustainable, long lasting, low energy cost. It is robust, low risk, unless you drop it, which is already installed. So it is very robust. You can use very, very strong chemical to do CIP, clean the place, soak with very strong chemical, and it doesn't affect the membrane, and you can get back your flux, your flow rate. Simple to operate, large channel for direct injection of coagulant. So just now you can see the channel is 2.5 mm, it won't be so easy to clog by the flux. So you can push it, and with the backwash of 5 bar, it will not clog the channel or the membrane, not like normal hollow fiber. If you put the coagulation assisted in hollow fiber, that if the channel is not big enough, so you may have that problem. You clog the channel, you clog the hole, not the pore of the membrane, but the channel of the membrane that go into the hollow fiber. So if you have a bigger channel, such as the multi-ball, so you will have some advantage like that. But the multi-ball, you may not be able to use polymer or organic coagulant, because it will blind the polymeric membrane. So able to treat very turbid water, such as backwash water. So able to couple with other technology. So if you put in PAC, because the big channel, it's easier to put the powder activated carbon, to couple with powder activated carbon. So, and it is easier to work with advanced oxidation, such as ozone and UVH2O2, which what they call producing the OH radical, very powerful oxidant. So if it is a polymeric membrane, so your polymeric membrane may be degrade or destruct, maybe damaged by the powerful oxidant, but ceramic membrane, it won't. So if you have wide range of raw water tolerance also. So it will also resolve the sludge schedule waste problem if you use the polymer. So here show the slide. This is the pilot test I have conducted. You can see the sludge if you use polymer compared to the PACL on the left-hand side. So you can see the water is separated, the sludge is sink. So you can decant, this one you can flow out from the tank or from the pond as a, to environment without any problem, but this one you will have problem to discharge. So it is not a scheduled waste in a way. So these are the advantages. So now we go to another section, which is membrane coupled with powder activated carbon. So this is effect, it will have some efficiency in removal of these organic pollutants. So especially this one, PPCP, just now we say is pharmaceutical and personal care products, and this ECD is endocrine disruptive chemical. So you have longer reaction time. If you put powder activated carbon in the conventional plant, you only have very short detention time or reaction time. Maybe it's less than, because you have to put it before the alum. So you do not have much time before the alum dosing. So, but you put it in this kind of membrane, you couple with the membrane. If your membrane is backwash every 2 hours, so your reaction time is from 5 minutes or 10 minutes and go up to 120 minutes. So it's very high reaction time. So it's very efficient in a way, for powder activated carbon to react in this way. So you also prolong filtration time and the CIP frequency. Why? Because the powder activated carbon also will take away so-called those foulant that will block the so-called membrane pore. So increased membrane filtration flux, that's what we have discussed. So is further. So utilizing pores in the powder activated carbon, if you have short detention time or short reaction time, so the pores, the holes in the powder activated carbon are not fully utilized, not fully used. So it's even better with the superfine powder activated SPAC, superfine powder activated carbon. It's even better result in this case. So I have tried something. If we put powder activated carbon into the system, so you can further remove turbidity from 0.16 to 0.07. You remove color from 9, if it is 9 only, then you move further, drop to 5. And also UV254 absorbent. Just now I already explained UV254 is like a DOC, dissolved organic carbon. So you remove another 20% more from here. So it is significant for the so-called turbidity and color and UV254 removal with powder activated carbon with the membrane. So membrane coupled with advanced oxidation, just now I say, is normally suitable for ceramic type of membrane. If you use polymeric type, just now I say, it may damage your membrane. So cannot, polymeric cannot stand the so-called the strong oxidant. So as I explained, the strong oxidant normally is this OH radical that oxidize the organics. It will destroy. It can remove endocrine disruptive chemical. Normally by destructing. Remove. It will destruct it will oxidize the so-called the pollutant, the organic pollutant. All those pharmaceutical, mostly organic. It will oxidize it and break it into smaller so that it will lose its original effect, right? So it also destruct algae toxin. So it will inactivate Cryptosporidium and Giardia cysts, in this system, right? But so note that AOP is not necessarily have to couple with membrane. You can have other system, right? But anyway, membrane will remove the C and G itself already. So but if you put the AOP after it, before it, or in any of the system, So it will inactivate the CNG. So these are another example that they install in, this one is in Netherlands. So 120 mLD, the ceramic membrane, but they install in a different configuration where you have 192 ceramic membrane element into one big vessel. So this is called ion exchange system. So they have the ion exchange first, and then they go to the, so this is, they call it the ceramic, this ceramic membrane configuration. Then after that, they will use the heat, this one UVH2O2, and then with the GAC. So in Choa Chu Kang, when they pilot, they were using the so-called ozone before the metawater ceramic membrane. So now they are installing 180 mLD. So ozone ceramic membrane. So this one, some pilot, recently there's another pilot done with a big configuration just now, the ceramic by this Spencer, published by this Spencer. So they use H2O2, static mixer, coagulation, and then immediately inject into ceramic membrane. So there may be residual ozone in the system, but it won't affect the ceramic membrane. So this is for secondary wastewater. So they found that, the result found that they can increase the flux. With the ozone, they can increase the flux into this range, that means 150 LMH to 250 LMH, where UF normally designed at 50 LMH. So there is an actual ozone ceramic membrane plant in Tokyo, which is 7 mLD, treating sewage water recycling for toilet flushing since 2010. So the photo is a bit small. This is how the plant looks like. So there is a system, the secondary effluent from here, and then the filter. So they use biological filter after that, and then they get into this so-called, they use so-called the pre-filter, right? Then they use ozone, and then from there they get into coagulation flocculation. Then they push into the membrane for reclaimed water. So this has been there for about 10 years, since April. So they give good quality water that complies with the Japanese and the international standard, and they are still ongoing at the moment. So these are the so-called advantages of the ceramic membrane. Right. So next, after the membrane, we want to move a little bit more from that, so which is the advancement of the water and wastewater treatment, which is so-called nanomaterial and water treatment. So this is actually a very big topic. Today, we have limited time. I only introduce a little bit because this one is concerning the next generation of the membrane. So before I get into the so-called membrane coupled with this nanomaterial, so I want to explain a little bit. Maybe some people are not familiar with what is nanoparticle. So it is a very high surface area material, very small volume. So normally in nanoparticle, which is 1 to 100 nanometer, is very small. So strong, stable, and durable. Material may change at nano level. So you can induce electrical, optical, UV, chemical, or biological property. So you make, this one will make chemical and biological react easier. So it can be so-called, it can be carbon, organic, inorganic, metallic, or ceramic. So the material can be ceramic. It means can be any of this material. So application in many fields, in electronics industry, medical industry, energy sector, and environment remediation. So we are part of water treatment, water and wastewater treatment, is part of the environmental remediation. So the nanomaterial for water treatment example, So this is carbon nanotube for desalination. So this is more what they call the one which is almost coming to industry, industrialized. Most of these nano material for water treatment are still in the laboratory and pilot. So only this one is coming, already have, but it's still fine tuning. So low electricity cost, how it works? So instead of very 60 bar pressure for the RO, so it is slightly higher pressure. So the first pass in higher pressure, it will remove 88% of the salt. Okay, the second pass, you pass through the so-called the nanotube filter, carbon nanotube filter. It will remove almost all the remaining salt. Right? So this is how it looks like. Top there, this is how the carbon nanotube looks like. So down there, how is the carbon nanotube filter looks like. Right? So it is being used in Israel and in America at the moment. Not fully commercialized yet. They're still doing fine tuning at the moment. So nano material for water treatment. So for example, this is zeolite, nanocrystal zeolite for specific cationic contamination. For example, this one you dose it in Malaysia also. Sometimes we use it. We put this powder, but maybe not in very fine in Malaysia, into our drinking water before the alum, so that it will remove the ammonia. So and some heavy metal. Right. So some are magnetic nanoparticle bind with oil, and it will bind. It will remove the oil and arsenic. Then by the whole thing we can separate by magnetic. Nanoparticle function as absorbent for targeted contaminant such as dye by this graphene. Graphene is a nanoparticle. So nanoparticle also can function as a catalyst to chemically degrade pollutants. So like titanium dioxide, for example, nanoscale titanium dioxide and zero valent iron. Those are the things they can use. So those are photo, titanium dioxide. So just for us to imagine, nanomaterial can be used as absorbent. So sometimes these absorbents are very high. For example, at the moment, activated carbon are normally the highest, in a very high range. We are talking about the so-called absorption capacity, absorbability, capacity is 300 milligram per gram of activated carbon. So it's 30%. But for this nanoparticle, it's a single layer graphene oxide. It can go up to 3,700 milligram per gram. That means it is taking 370% of this body weight, if this mass. So can you imagine? So you can see the ultra space. So you can take can take oil. This is one of the method. This is how it looks like. So membrane coupled with nanotechnology. Normally, now the most popular one is to combine nanoparticle with polymer. So it's called nanocomposite. Right. So this nanomaterial combined, such as we use just a carbon nanotube, zinc oxide, graphene oxide, titanium dioxide, and so on, silver, copper, 2D material or novel, this one. So fine-tune the structure and the structure of the membrane. You fine-tune the structure of the membrane and physiochemical properties such as porosity, hydrophilicity, antibacterial, thermal stability, chemical characteristic, electrical conductivity. So some nanomaterial of the membrane, you can use electrical to induce it so that it will remove the foulant or some reaction on the foulant, and you'll continue to this one. These are on the lab scale and pilot scale. Enhanced rejection, suppress accumulation of foulants. So you use UV or something else, it will oxidize those foulants, and it will also antibacterial. So that's how it works. Instead of you put what we have shared just now, you are putting in the coagulant or polymer. So now this one embedded or coated all this nanomaterial together with the membrane. So in this type is they are using nanocomposite. The nanocomposite means they combine the nanoparticle, the material, into the polymer, blend into it, and then they make into membrane. So this is one example. They use carbon, this is nanocomposite membrane. So this one, they use carbon nanotube, very fine carbon nanotube embedded into, this is the polymer matrix. So they put all this into it, right? And then the oil, so this the orange color is the oil, the blue color is water. So all the water will pass through whatever way, it will be enhanced and pass through. So the flux will be higher. And then the so-called the oil will be this one. So it will be increased the so-called the hydrophilicity, flexibility of the membrane. So the flux will increase in this way. So these are the example. So nanoparticle membrane for water treatment. So these are ongoing. So desalination, University of California, and so-called Nano H2O, this company. So they are something ongoing with the Korean company in Korea. So they use nanopore membrane for desalination. They make the membrane with very, very tiny pore. Just now I already mentioned, RO is actually not so much of straining or filtration actually. So it's actually work on some surface tension principle. You press on, then you take the water. But this one is really the nanofiltration for desalination in this kind of so-called nanoparticle membrane is really filtration. That means actually only water molecule will pass through. Okay. So why RO? If your household, after your RO filter, you see another activated carbon filter, right? So that is because in the RO system, actually the pore is quite big. There are some organic material will still pass through. Although they can so-called retain the molecule of sodium and chloride, but organic will pass through. For this case, only water will pass through. The nanofiltration, with nanoparticle membrane is very interesting. So other method is so-called to coat the membrane with titanium oxide. Coat the membrane. This is an example of coating with the titanium oxide. So titanium oxide is a very powerful oxidant. So it can in situ oxidize the foulants. It will become self-cleaning and enhance continuous flux. So you see in this picture, this left-hand side, this one is the original membrane. So they start to put in the thing, and then it will cover, the membrane surface will cover with this titanium dioxide. So it will one way, the pollutant, what they call, before they can blind or foul the membrane, block the membrane pore, so it will touch the titanium dioxide on the surface of the membrane, and then it will get oxidized, become a much more smaller particle, if it is still there. So then you pass through the membrane instead of fouling the membrane. That's how it works, right? So there are actually many today, because there's time constraint here. So these are all the examples under study. For example, for UF, they are using something, they are using what they call zinc oxide to do something and so on. So you can see there's a lot, we cannot finish the example. So actually this topic we need at least another web binder to talk about nanotechnology for water treatment. But anyway, all this, most of this nanotechnology for water treatment, beside the the carbon nanotube for desalination, most of it are not commercialized yet. They are still in pilot stage. They are still in tuning stage. Even the carbon nanotube, is considered already they have the plant, but they're still trying to do some so-called fine-tuning. So, to summarize, coagulation assisted membrane filtration is one of the enhanced sustainability technology. So benefit, it will increase the flux, lengthen filtration time, CIP, and membrane lifespan. And also it will ease for the sludge treatment or the concentrate treatment. So there are advantages of ceramic membrane, but it's more expensive. So polymer membrane now, they are getting bigger and bigger modules so that they can put in more fiber. So they are fighting with the ceramic membrane very fierce now. So maybe they are equivalent, or they may be getting better in the market, which is possible soon. So now with this nanoparticle and nanocomposite, this one, it will be, much advanced. It's upcoming, in the treatment of water and wastewater soon. So in fact, in some of the very small scale, third world country, they are already using nanoparticle for water treatment, but in a very small scale. Like they treat something, they want to drink some water, they put the nanoparticle in, and then they shake the nanoparticle in the bottle, and then let the thing settle, then they can drink the water. The nanoparticle will remove all the pollutants. So they drink the water, then later they do the same again in another water. But it's not commercialized, but it will help the people. That is an example how they use the nanoparticle for water treatment in third world country. So we hope to see nanoparticle become affordable and sustainable soon. Like what I say already, some utilized in third world. So with this, I end my presentation. Thank you for your time and patience. I already exceeded some time. Thank you.
Thank you, Dr. Wong. I think you can stop your screen share.
I can't.
Okay, we have done it. We've done it for you.
Yeah.
Okay, so hi everyone. So we're going to take a very short break, 1 or maximum 2 minutes. Maybe you can make yourself a cup of coffee, or you can go to the washroom. So we'll use this 1 or 2 minutes for Dr. Wong to review the questions that you have sent to him, and also for attendees who would like to post any questions now. So click, so I can see some questions coming in. More questions are coming in for Dr. Wong. Or you can click on the Q&A, you can review the questions.
I'm looking at it now.
Okay. So we'll be back in 1 or 2 minutes, everyone. Do you want to start now, Dr. Wong?
Okay, I can start.
Okay, so yeah, so you can click on answer live.
Yeah.
Question that you want to answer.
Okay, I just start from the beginning. Okay, the first one,
Right.
you say, you have mentioned membrane can use for total phosphorus and total nitrate removal in wastewater treatment. As far as I understand, in wastewater treatment, total phosphorus and total nitrogen removal are removed biologically, chemically. Can you please clarify how membrane can remove this one? Thank you. So, with what this person say is Adeline Chua. So the question from Adeline Chua. So what she say is correct. So in the removal of total phosphorus and this nitrogen, the biological process or chemical process will do. But in, like, for example, if you want to have even higher water quality, because with the chemical, that means biological, that means you are settling. You're using settling. So settling, that means there will be some particle still inside the water that discharge. If you use membranes, all these particles will be removed. It means all these particles will still contain some total phosphorus and total nitrogen. Just like our experience in China, when you use MBR compared to we don't use MBR, the result is different. The water is crystal clear, and the total phosphorus and total nitrogen is low. You know, just imagine if you can see the wastewater treatment plant, the wastewater coming out, treated wastewater without membrane coming out. Some are very green. Why they're green? They're all algae. So when you have all algae, you test for total. I mean total, not dissolve. Total, that means the algae cell will have all this phosphorus and nitrogen. Okay. So the second question is from Dr. Lim of this SSB. So, so I know that it is I know that what is may I know what is the average cost of production of drinking water using ceramic membrane through MF and RO in Malaysia? So now the price is already changed. So depending on the size, because for ceramic membrane, the cost is more on the capex. So if you take the capex into consideration, so the cost will be high. So if you don't take capex into consideration, so the cost is slightly higher than the conventional only, because what you do is conventional, you pump one time. For ceramic membrane, your cost is your energy cost, because the coagulant is the same. You do conventional, you use coagulant. So, but with ceramic membrane, your so-called conventional system will remove, and then the settling tank, flocculation tank, this will be replaced by ceramic membrane. But the main thing is the capex of the ceramic membrane is high. If you put into it, it will be higher than the conventional, of course. The difference is on the energy cost to push in and some CIP cost to clean the membrane. It's not very significant. You're talking about additional of 0.2 kilowatt hour per meter cube only. So a little bit more on the chemical cost. So RO, if you're talking about RO in Malaysia for desalination, if you use TMB electricity, you are talking about like 3 ringgit and 50 cents. If you use diesel to generate the RO, you're talking about 4 ringgit and 50 cents. Normally, people use RO in the island, you're talking about 5 ringgit per meter cube for RO. Okay.
Dr. Wong, can you turn on the video now? Can you see your video icon, bottom of the screen on the left?
Okay, I can see now. Yes, I can see now.
Okay.
No, it
Yeah,
was
so
covered
we
by
can
the
see you.
computer. I don't understand.
Yeah.
Yeah,
Okay.
yeah. Just now
See you now.
I can't. Yeah. So okay. So this one already done, but I can't see the type answer. So I already answer. So sorry. So that was answer live already. Yeah. So I've done. So the next question. So the next question. Does coagulation, this is from Yusuf, does coagulation assisted membrane require coating of membrane surface with coagulant? That is not coating. So you just inject the coagulant together with the raw water only. So that means you mix the coagulant into the raw water before you inject into the membrane. It is just that simple. No need to do coating, right? It's very simple. Thank you. So the following question, I would like to, this is from VJ. I would like to ask regarding the impact of coagulant on the long-term stability flux of membrane. You have mentioned that the permeate quality was improved as a result of the coagulant formed on the membrane surface. So will the coagulant negatively impact the water flux for long-term operation, which significantly so-called reduce water production capacity? So this one, it will not. It is proven that people use coagulant assisted, say for example, the ceramic membrane, especially, they are using it for 20 years already. There's no flux declining. Okay, no flux declining. So if you can recover, it's proven is you can recover 100% for your flux. There's no effect on it. The coagulant have no effect on it. But this have to be careful. If you are using polymer or organic coagulant for polymeric membrane, that can be very, very dangerous. You get what I mean? So that is different. If you use ceramic membrane, it has been 20 years proven no effect. You know, if you are using polymeric membrane, don't use polymer, don't use organic. You use inorganic. That means alum and PACL. You know, it should not. Right? Thank you. So the following question: how you see the membrane technology can be adopted in Malaysia municipal water market, since most of the consultants in Malaysia have more prefer towards conventional system and conservative thinking when come to this system design. I think the consultant is, in a way, you know, they do not have the preference toward conventional system, I think. So it is the client that prefer the conventional system because it is cheaper, right? So whether your question is called can be adopted, it can be adopted, but it's just that the cost is higher. Whether like the operator, because now for example is all the cost is parked under PAAB. So whether PAAB agree to use the membrane or not, that is very important. Unless the plant, you know, the water is highly polluted, then it is a different story, right? So that is my view. So otherwise, if it is not so polluted, you may not use, you know, you may not, if the water is very clear, you may not use membrane. But in Malaysia, is sometimes it's the other way around. So we have water which is not polluted from the stream, but in Selangor, they use membrane. There's two membrane plant treating very clean water in a way. So, but I think if you say can be adopted into Malaysia, I will say yes. It is very much depending on the cost, whether people are willing to pay or not, whether the tariff can sustain or not. All this will have to come in, right? Thank you. Next question, I also answer live. Can membrane technology ceramic or others, remove ammonia and nitrate in water? The answer is no. The ammonia will pass through all this. Even the ammonia can even pass through RO. So membrane cannot remove ammonia, and nitrate in the water. So if you want to remove these two, you have to use ion selective resin or some other technology, not membrane. Right? Thank you. The next one, water therapy is one of the cheapest in the world. How can this support the advanced technology in drinking water treatment plant? I think this question is we leave it to the future. That means one day when we realize that we have all these pollutant, now the water tariff so low is actually the government is subsidizing. So until one day we're realizing subsidizing water is not sustainable, we should pay the real price, then it will come in. That's what I can say, right? So this engineer here, what is the average CapEx cost per meter cube for using ceramic membrane with organic coagulant for plant of say 20 mld, and what is the CapEx for 20 mld plant, and what is the average life of ceramic membrane? Sorry, I didn't type this. Can you see the question? Yeah. So Mr. Yi, this engineer Yi is from BAB before. I shared with him the ceramic membrane, I think 7-8 years ago. So if you talk about the OPEX of ceramic membrane, just now my slide, I think will show about 30 now maybe it's more expensive. 30 cents is like a long time ago, is like 2013. So we are talking about 40, maybe we are talking about slightly higher, about 40 cents. The OPEX is not very expensive for ceramic membrane. So for 20 mld small plant, based on my just gut feeling, the budget, gut feeling last time, the cost for 100 mld, we are talking about somewhere around maybe 50 to 60 million, depending on the water quality. This one, if the water quality is from the dam, it's more expensive. If the water quality from the Turbid river is less expensive. So it is maybe, it can be, you're talking about the process alone, it can be 30 to 60 million depending on the water quality. So what is the average life of ceramic membrane? Now the ceramic membrane has come to 20 years actual record. So there's no breakage, they are still, in Japan, they are still using it. So maybe, I may say maybe 25 or 30 years, ceramic can last very long, but maybe I will ask the Meta Water, but I did ask them last time. They are also not so sure how long it will last, but at least 20 years, I would say. Next question from Jamie. Can the residual or antibiotic be removed using nanoparticle or nanotechnology? So if you ask me, I would say definitely yes lah. So, but you may need to do some pilot tests. Which type of nanoparticle you get? Once you get a suitable one, you will do. Next one, from Muhammad Ridwan. I have few concerns regarding your topic. How can you ensure that the coagulated waste does not foul the membrane? How frequent the membrane is needed to be backwashed? I always forgot to press the answer live so you can see the question. Okay. It's a good question. How can you ensure that the coagulated waste does not foul the membrane? I can't actually ensure, but we have pilot. We have pilot on the water and wastewater, both. But it depending, you know, for drinking water, we can see, you know, we can see for drinking water, it so-called the particle, you know, it won't really foul the membrane for sure. For waste, maybe there's some, you know, depending on what kind of wastewater. So in the pilot, as I have said, you know, the frequency of backwash is with the coagulation assisted, you know, we can move from like 30 minutes to 120 minutes. So that is the frequency. That means every 2 hours I backwash. Before, you know, without, you know, before I'm using a hollow fiber, every 15 minutes I can see the flux almost, you know, very low already. I left 10% of the flux, so I have to backwash it. So it was 15 minutes, something like that. Thank you. Next question. This one is anonymous. What is your opinion on the idea to incorporate photocatalytic like titanium dioxide into membrane for water treatment, especially for drinking water? What about the leaching of the photocatalytic into the purified water? Wouldn't it be dangerous to human health? Sorry, again, I forgot this one. Okay. Your first question, what is your opinion on idea to incorporate photocatalytic? So I am not sure. I think to so-called coat this titanium dioxide on a hollow fiber is a little bit maybe really difficult, but people are already in pilot that they can coat into the flat sheet membrane. So with the flat sheet membrane, it's easier to use UV to shine on the titanium dioxide and then it react. So, you know, if titanium dioxide, once they get UV light, so they will become very oxidant. And this in the laboratory, you can oxidize the tea into mineral water, for example. You know, looks like mineral water. Of course, what you're concerned later is the residue. Now, when we talk about all this, say for example, I take a very extreme example. Say for example, microcystis, the algae toxin. If you drink the algae toxin, you either got liver cancer, kidney cancer, or you can die. You know, if the concentration is very high. So, but with this kind of arrangement, once you oxidize the, say, microcystis, so the microcystis from a very large mega molecule, they break into smaller one. So this one is less toxic. So there is the toxicity effect is gone. This one people already study how to oxidize all those algae toxin and treat the water for drinking. So once you have that, you know, it is normally less dangerous than before. Of course, you don't treat wastewater that you can oxidize something into dangerous. That is, I'm not so sure. Normally, you oxidize something, you break into smaller one. Say, for example, the toxic, you have less problem. You know, maybe you can tell me there's anything that you oxidize and then later it become more problem. That can happen, but not that I know of at the moment. So thank you. I think this is last question. I will answer live as all. What is your opinion on the idea? It's the same. It's the same question. Into membrane for water treatment, especially for drinking water. What is the opinion of the leaching of the photocatalytics into the purified water? Wouldn't it be dangerous for human? So maybe you can send me some email. We can communicate. You know, if you have further question on this, I can see how I can assist you, or we can discuss. That's all. Thank you for the time being.
Thank you so much, Dr. Wong. So, Amy, do you have anything to share?
I have no more.
Yeah, thank you, Dr. Wong. So we just want to share this slide. which is an award that ProTem is organizing, the MTE 2020 COVID-19 International Innovation Award. So if you have an innovation or a initiative that you have carried out during this COVID-19 pandemic, you can join this award. So you can follow us on our Facebook, Malaysian Technology Expo. So thank you everyone. And I'd just like to announce that our next webinar, which will happen next Tuesday at 3 o'clock, same time, is going to be presented by Professor Dato Engineer Dr. Bakar bin Jaafar, Chairman of Malaysian Green Technology and Climate Change Center, now known as MGTC. Dr. Bakar is also a professor at the UTM Perdana Center. And his topic will be conversion of excess pressure in water supply distribution networks into power and hydrogen fuel. This is, of course, another hot topic. So I hope all of you will join us again next Tuesday, same time, 3 o'clock. Mr. Lee Kunyu, is there anything you want to say before we close?
No, thank you.
Yes. Okay, so we want to thank Dr. Eddie, who has spent so many hours of his time preparing for today's presentation. So we'll see you next week again. Do follow us on Malaysian International Water Convention Facebook page. That's where we will put all our announcements and our links to our YouTube channel where you can watch all our videos on demand. Thank you again, everyone, and see you next week again. Thank you, Dr. Wong. Thank you, Mr. Lee.